Our next speaker is going to be Sebastian Torres. He received his bachelor's degree from the National University of Mar del Plata in Argentina and his master's and PhD from the University of Oklahoma in electrical engineering. And after that, he joined the SIMS, and he's now the assistant director and a senior research scientist and the coordinator for NOAA operations. He's affiliated with the National Severe Storms Laboratory. He's received the 2016 Dean's Award for Outstanding Service, the 2011 Department of Commerce Gold Medal as a member of the Radar Research and Development Division at NSSL. He's also an adjunct faculty member in the School of Electrical and Computer Engineering and a graduate faculty at the Advanced Radar Research Center at the University of Oklahoma. And he is going to be talking to us about various activities in radar engineering.
Thank you, Greg. Okay, so good afternoon, everybody. We switch gears a little bit now and talk a little bit about engineering. It's really an honor for me to be here doing this review of the last 40 years and talk a little bit about the future. It's also a challenge because I've been with SIMS a while, but not for 40 years. I was 7 years old when SIM was created. Of course, it took me a while to get here. But luckily, I've been able to experience firsthand most of the engineering accomplishments that were done in the field of radar in SIMS. So what I did for the 20 years or so prior to my time was I went back to the written sources, the reports, the SIMS annual reports, the NSSL reports, and I went back to the gurus, Dushan, Alan. They helped me put together some of this history prior to my time. So since we're switching gears, I thought I would remind people what engineers do. We're not chasing storms. We're not enamored of that tornado vortex. But what we do is, and I highlighted some of the keywords here from Wikipedia. Engineering is the creative application of science to the innovation, design, construction of systems, radar systems in our case, for the benefit of humankind. And when I saw that, I was like, this is the perfect example of that. What we do benefits humankind. In terms of weather radar engineering, I'm going to focus on 4 areas. And under software infrastructure, signal processing techniques, and under hardware, a lot of work on radar systems and radar technologies. So I apologize in advance if I left out a particular project that doesn't fit this. I also have limited time, so I'm going to touch on just a few of the projects that sort of highlight SIMS contributions over the last 40 years. Let's start with some numbers. I think it helps put things in perspective in terms of the timing and the scope of SIMS contributions in terms of radar engineering. If we look back, we can see that the Doppler weather radar research and development theme was added in 1996. I went back through the SIMS annual reports, and if you look at 1995, you don't see the Doppler weather radar theme, but you see it in the 1996 report. But there's some evidence of radar research and development before that time. So I think we were doing things before that time, and then the theme became an official theme of SIMS. In 2011, the name was changed to just weather radar R&D. Obviously, we had done Doppler, we had done dual polarimetry, we were doing phased array radar, so it was time to just make it more generic. Now, if we look at the National Severe Storms Laboratory's radar division, we can see that 70% of the employees are SIMS employees. And now if we dig deeper and look at just the engineers, 14 out of 18 engineers in RRDD are SIMS employees. And if you look at, for example, the Advanced Radar Techniques team that I lead, all of us are SIMS engineers. So that tells you how much of the accomplishments in radar engineering that come out of NSSL, for example, are also a result of the SIMS partnership. So I went back in time, like I said, and I was trying to find what is the first contribution by SIMS in the area of radar engineering. And Dushan pointed me to this report. Here's a SIMS report, number 71. This is when we were numbering our reports sequentially. I don't know what number we would be at right now. And this is from July of 1986. M. Sachidananda here, or Sachi, was affiliated with SIMS at that time. And what Dushan and Sachi did was they took Cimarron, which was actually the first research radar that could do dual polarimetry, and they implemented the computation of the polarimetric variables in real time for the first time. And here we can see, for the engineering geeks in the audience, the spectra of the H and V signals from that radar. So this is amazing if you think about the fact that this report was typed with a typewriter. So to have this type of data in real time was a really fantastic accomplishment. Since that time, from 86 to the mid-90s, I couldn't find a lot of evidence of contributions in radar engineering. Dushan pointed me to a couple of people, also researchers from India that came to SIMS perhaps for a short period of time. There's Balki, there's Mahapatra. They all came for short periods of time, but things really stepped up, as Pam mentioned, after the deployment of the NextRad network. So we fast forward about 10 years and we get to the mid-90s when SIMS was heavily involved in the development of the WSR-AD-AD open systems. And here I'm giving you 3 keywords that are confusing everybody. So I thought I would use an analogy to describe what open systems is supposed to do. So let's say we have an old recipe box, and in this analogy, the box would be the hardware and the recipes would be the software. So let's say, you got this recipe box from your grandma. The recipes are a little bit outdated, but you want to keep some of them. You want to get new ones. So you go to the store, you get recipe cards, and they're vertically oriented. So they don't fit the box. So this goes to the issue of interoperability. If you do not have the ability to use recipe cards from another vendor or another source, you cannot insert new recipes into your box. Let's say, on the other hand, that you're tired of the box, the painting is chipping and the lid doesn't stay open, so you go to the store and try to get a new box, but the box is a different size. So there's no way you can transfer your old recipes to the new recipe box without, for example, having to retype all of them. So that goes to the issue of portability. So if we cannot use 2 different boxes with the same recipes, that is, 2 different computers, for example, running the same type of code, then we have a problem, and this is very, very frustrating, as the young Eddie Foreng is showing here in this picture. So now going back to reality, in the mid-90s, we have, in 1997, is when the last WSR-AD-AD radar is installed as part of the NextRad network. Now we rewind a few years back, and even before the National Weather Service was done with that installation, they realized that in order to support evolution of the system, to keep up with new technological upgrades, they had to do something about it. So they embarked into the Open System project that aimed to replace all the computing infrastructure with open systems that allow you that interoperability, that portability that were based on open standards. I know we can argue whether they really accomplished that or not, but that's a separate discussion for when we go to the poster session if you are interested. But I'm going to highlight that SIMS contributed significantly to the Open RDA. So we retrofitted the KOUN radar, our research radar, and upgraded all its computing capability to be based on open systems. I was part of that project. It was actually the first dual-pole WSR-AD-AD radar, and it was the proof of concept for a future upgrade of the network. There was also the OpenRPG project that aimed at replacing the second block, the radar product generator, actually the RPG is in use today. And it's the system that runs all the algorithms, like tornado detection algorithms, quantitative precipitation estimation, and it also serves as the user interface with forecasters and allows forecasters to control the radar, to operate the radar. And finally, there's OPUP. OPUP was a little bit of an obscure project that only the DoD funded, but OPUP is basically a system that captures all those products and archives them and makes them available to the Air Force. And so that was also another big project that where SIMS had a big part. So now, going to the signal processing techniques, I also wanted to introduce what signal processing means. A lot of people in the audience may not be familiar with this term. So basically, if you look at the radars received by the signals received by a radar, they would look something like this diagram on the left. Basically, it's a lot of data, incomprehensible. What signal processing tries to do is to convert that data into usable information, usable to the forecasters and algorithms, models, things like that. And Jeff Kimple, when we were doing the lab review, one time said, radar signals are messy. You have to emphasize that. So here is the message again. Radar signals are very messy because in addition to the rain, in the same area the radar is looking at, you may have other things like trees, terrain, planes, towers, and all of these things need to be removed. The data needs to be cleaned up, as Pam mentioned before, and not only for the forecasters, but also for the models, for the algorithms. So here comes our geeky signal processing superhero to take all of that away and clean up your radar signal. I'm going to show you some examples of that. For example, getting better velocity data. Here's a Doppler velocity field. The red colors indicate the wind is moving away from the radar. The green colors indicate the wind is moving toward the radar. And you can see some situations where greens and reds are next to each other. And you can tell that nature is not doing that. This is a problem with how the radar is processing the data, but if we use one of our super techniques called staggered PRT, we can clean that up very nicely. Here I'm going to go back and forth again. A staggered PRT is actually a technique that was developed here and actually in a way that could be implemented operationally on the Nextdoor network and actually has been transferred to operations. It's not operational yet, but it's in the process of becoming operational. Another example is contamination from echoes from the ground. You can see here in these panels of reflectivity, velocity, differential reflectivity, and correlation coefficient, how you can see some elevated echoes close to the radar, and also you can see some footprint corresponding to terrain. It's very dramatic in correlation coefficient. You see it, it stands out very clearly. Now, if we apply our super techniques, wet and clean AP, you can see how that contamination goes away. And this will be very useful if you're doing, for example, precipitation estimates, because you're not going to count rain where it's not raining, for example. We developed wet and clean AP solely within SIMS. Actually, we have licensed clean AP to a private company, and we actually transferred clean AP to the UK radar weather network of weather radar. So we have transferred it to our National Weather Service, to a foreign National Weather Service, and to a private company. This is also an example of how SIMS connects to government, nationally, internationally, and also with private companies. In terms of reach to operations, here's a number of techniques that we have either transitioned into operations, that we are currently in the process of transitioning them, and some that are just in the research stages. R2O is a very key mission that SIMS fulfills in helping the NOAA mission. And you can see, for example, here systematic phase coding was operational in 2007, but the first report that shows some research in this area is from 1997. So 20 years of research before this technique could be implemented operational. So the other techniques, again, CBT, also developed by SIMS researchers, radar noise estimator also. So a lot of contributions in the area of signal processing. So we have a number of geeky superheroes in the audience. Radar systems, also big in terms of SIMS contributions. We have KOUN in the mid-90s. Again, like I said before, the first WSR ADAD radar that was a dual polarimetric radar. Pam talked about the National Weather Radar Testbed, the first phased array radar that was used for weather observations with a lot of important results. As Pam mentioned, we have also strong involvement in the development of NOXP, a mobile X-band dual pole radar that participated in a number of campaigns. And more recently, the 10-panel demonstrator, we did not develop the system, but we did a lot of engineering research with this system to understand how one could calibrate a phased array dual polarimetric radar. So a lot of research and development in terms of systems here. I'm going to talk a little bit about our phased array radar because it's, it's part of our history, but also a huge part of our future. As Penn mentioned, from 2003 through 2016, we have what I call the legacy NWRT PAR, and that supported a lot of interesting demonstrations. Pam talked about the rapid updates. Here I'm showing again an animation that Pam provided with PAR versus conventional radar. We also were able to demonstrate that you can scan not in the usual way, but you can adapt to the storms that are out there. And you can have faster update with some storms and slower updates with other storms. And we could also show that a single system could be used with two functions. The weather surveillance function and the aircraft surveillance function were combined, and here you can see displays of reflectivity data with aircraft tracks intermingled. So a lot of important things were done with this system. But if you were to look inside the radome back then, you would have seen a system that was based on outdated technology, that was a passive array, and also used single polarization. So what NOAA decided to do in collaboration with the FAA was to trash that antenna, even though we loved it, and replace it with one that uses modern technology. It's an active array, and it's dual polarized. So SIMS has been very involved in this process. It's a $38 million investment from the FAA and NOAA, and we collaborate with other government, industry, and other universities. So very, very important. In terms of designing the radar of the future, when we cannot build a radar, we have to simulate it. So there's a lot of expertise within SIMS in terms of simulating radar systems. And I'm running out of time, so I'm going to accelerate a bit. And so to look at the future or to foresee the future is important to look at their past. And we can see through our past that we have been part of all these revolutions in weather radar observations, from the addition of a network that produced reflectivity data to the incorporation of Doppler, velocity, to the dual pole. And so what's next? Obviously something related to phased array radar. Is it MPAR? Is it NextPAR? Is it MPAR? All these acronyms are being thrown out right now. Something that would be beneficial for the forecasters and also for the prediction, for the models as well. So my prediction for the next 40 years is that we're going to be investing a lot of time and effort on making operational use of phased array radars. Right now it's being used for research. We want to address the technology obsolescence of the current system, and we also want to, of course, improve weather surveillance. We want to fill observing gaps, retrieve data, other kinds of data from the radar data, and also we want to go perhaps into hybrid observing system networks to improve the quality, the coverage, and the availability of radar data. To end, I'm going to say that the partnership between OU and NOAA is the perfect partnership to save lives and property. Thank you.
Okay, we have time for questions. Okay, yes, Marion.
You want to comment about in the next 40 years with regards to all digital phased array radars?
Yes. So all digital architecture is an architecture that, let me backtrack a little bit for the people who are not fully familiar. A phased array antenna is composed of thousands of smaller antennas. So if you have an all digital architecture, that means that you have thousands of radars actually that are digitizing the signals, and then once you have digital signals, you can do a lot of things. The problem right now with that is that first, it hasn't been proven. It's being proven by our community, but it hasn't completely been proven. And so but on the other hand, the capabilities that kind of architecture would provide are really, really important to the National Weather Service mission. So in terms of providing calibrated, good quality, dual polarization data, it's very important. So I see, for our future, I see us looking into, of course, that as an option, and as we move forward, obviously technology costs are going to decrease, things are going to be, things that right now seem to be impossible are going to be feasible. All we have to do is look 10 years back and look at the technology back then, and so it's very easy to see that in 10, 20 years, things like an all-digital phased array radar would be possible.
Okay. Any others? Well, let me ask, do you think, we've talked about phased array radar in the next 40 years, do you think there's any other new, unique observing capabilities that might be complementary with the use of phased array radar in the next 40 years?
Well, when we talk about radar coverage, it always, the idea that we're not really observing what's happening close to the ground, especially when things are far away from the radar, that makes us think that we need to fill those gaps. So there might be, ways to fill those gaps, maybe not using phased array radar technology, but using conventional technology. We can also go into other ways of getting useful data, for example, using communication links. That's one of the ideas that is being proposed currently as something for the future. Also the idea of having radars on balloons, stratospheric balloons looking down and kind of complementing observations from the ground. So I think, there's a lot of things out there that in the next 40 years, who knows? Right now they appear to be esoteric, but, it's a matter of time.
40 years is a long time. So anyways, let's thank Sebastian again.